Hello, everybody. Today we're going to talk about reading tables, basic tables. This assumes that you already know how to run t-test and why you run t-test and how to run Anova, which is analysis of variance, and why you run Anova. Now I will, explain some of it here and there, but the whole portion, the majority of this video assumes that you already know how to do it. So as you can hear, probably there's a background. My son is watching TV, but that's live during coronavirus. And we're recording those videos while trying to entertain children. So without further ado, let's get going. So first, every time before I actually run any analysis, I'd like to look at the variables I am dealing with. So let's run basic statistics, basic descriptives. And here's the thing, when I approach running analysis, I sort of go ahead and run all measure of central tendencies and dispersions of my interest, even though I technically, in theory, in practice I do, but in theory, let's assume I don't actually know the level of measurement of these variables. So some of my measures of central tendency, like mean, median, mode, may not be appropriate for a particular variable due to level of measurement, but I still go ahead and run run them all at the same time just to save time. And I'll explain more as it shows up. So let's just look at some of these basic variables here. These are observed variables. None of these variables are latent, so they don't need multiple measurement. Just a very basic observed variable. So I'll just look at all of them at the same time. I move them over. And like I said earlier, I typically ask for, you see, central tendency, mean, median, mode. I don't usually ask for sum. And then dispersion, I like to ask for minimum, maximum, standard deviation, sometimes variance. But I typically deal with standard deviation. So like I said earlier, some of these may not be appropriate for the levels of measurement that we're dealing with, because not all of the variables will be of appropriate level of measurement for, say, mean, which is appropriate only for interval or higher level measurement. So continue. And okay. So this is some of my previous analyses. I apologize. So let's allow the computer to run it. Now make sure you can see it. So you can see years with supplier. How long has your company been working with the supplier? There are 274 valid cases, meaning 274 participants filled out this question. The average is 15.67. But before we really start about averages, let's check and make sure that the level of measurement is appropriate. So here is a frequency table for years with the supplier. And as you can see, it is in basic years, so there are no ranges, not 1 through 5, 6 through 10, which ranges would be ordinal level measurement, but because this one is just raw observation of years, this makes it a ratio level of measurement, because 0 means absence of phenomena, the increases are equal, and so on. So this is ratio. So because years with the supplier is a ratio level measurement, we can actually talk about things like mean, median, and mode. So an average time, or yes, average years with the suppliers is just over 15 years, so it's quite lengthy. Median is 14, and 15 is multimodal, meaning there's more than one mode, as you can see by this A, which tells you about that there are multiple modes. You can sort of see 15, that 30 observation. You can also see 20 years has 30 observations, so means 20 is also a mode. So these are the two top observations. So multimodal, actually bimodal to be more specific. There are two modes, one at 15, one at 20. Next, so average is 15 years, and it ranges from 1 year, less than one valid percent. So there are two observations that were 2 years with the supplier, all the way to 75 years, which sounds a little crazy. Has only one observation and 0.4 valid percent. Okay, with an average of 15.8 years according to this statistics table. Now let's look at gender. Gender here, let's scroll down and look at the frequency table. So gender, ownership gender is coded as 0 for female, 1 for male. The 25 females, 249 males. Talk about a male-dominated industry. So we have here 25 females, 25 males, which obviously gender is a nominal level measurement. So, which means mean and median are not really appropriate measures of central tendency. Mode is. So 1, most frequently occurring, would be male. Okay? So standard deviation is not appropriate either. Minimum, maximum are appropriate, but there's not much. 0 is the lowest, 1 is the maximum. So, I mean, it's not rocket science. So this is what I mean when you read a table, you have to pay attention, even though you may have asked about all these measures of central tendency and dispersion. You can ask SPSS to do it, but it may not have a meaning. So here, gender mean, so average of 0.91 has really no meaning. You know, it's tending 1, which is coded for males, but really has no real meaning. Whereas here, years with the supplier, 15.68 years with the supplier on average, makes a whole lot of sense. So it's appropriate, it's a ratio level of measurement, it's appropriate to talk about this. Okay, so let's run a quick t-test between gender and, let's say, working in industry, work in industry, years worked in industry. So years worked in industry, I believe, is also a ratio level measurement, but let's check. Time spent browsing. Worked industry, years worked in industry, that's this variable. And it is ratio level measurement as well. No ranges, no trickery here. So let's run a t-test. Let's run a t-test for gender and years worked in industry. So usually you would have a set hypothesis before you run this sort of test, and you may say males. Your research hypothesis would be that there is a difference. Let's just do difference. There's a difference in years worked in industry between males and females. Okay, so you're expecting different mean for years for male versus female. So male versus female spend different amount of time in industry. So the null hypothesis would be the opposite, that they have spent the same amount of time. Now, when it comes to directional hypothesis, so this one was non-direction. We said we really don't know where the difference is, but we think there is a difference. If we were hypothesizing that, let's say, males have worked more in the industry than females in terms of years, our null hypothesis would be the opposite and covering all other alternative solutions, meaning if we hypothesize that males work more, our null would be that females would have worked less or equally as much as males. Okay, so your research hypothesis tends to, set something you want to test, something you think is right, and then the null sort of covers all other alternatives. Okay, so let's run it. Again, I assume that you already know how to run t-test. So we are running it's a mean test. And I'm going to use gender as a predictor. And I previously checked that it is coded as 0 and 1. And this is important to know because you will have to specify the groups in your independent sample t-test. You will have to specify your coding. And my test variable was worked in the industry. And I'll keep it as is. Don't do anything here. Hit OK. So again, remember that we are testing, and I'm going to make a note here so you remember and I remember we're testing hypothesis research, really. I should say research hypothesis or alternative research hypothesis that there is a difference between males and females in terms of years working. And here's a little problem with this, because we really are looking to have a fairly equal groups. These groups are definitely not equal. They're tending to male, but we're just going to disregard it for now. But keep in mind, in an ideal scenario, you'd like to have these groups fairly equal. The first step that we have to do before we do anything, before we really move on to the test, is look at the mean. First, females. Let me fix this because it bothers me. First of all, we hypothesize that there's a difference. If we hypothesize that male work more, we would make sure that our mean is in a direction hypothesized. So again, if we hypothesize that males spend more time, we would see that this is in line with our hypothesis. It seems that males spend more time and have worked more in the industry than females, so we can continue. If it was opposite, we would not continue. But in our instance, we have a hypothesis there is a difference. And so it appears to be a difference, but we cannot make this conclusion until we actually run the test. So before we can run the test, we can draw any conclusion based on this data. We have to make sure that we are not violating the assumption for t-test. The assumption for t-test is that there's a homogeneity of variance. In other words, the variances for on this variable, this outcome variable for each group can be considered equal. Okay, so our null hypothesis for Levine's test is that the variances are equal, and the alternative hypothesis for Levine's test is that they are not equal. This is one in very rare cases when we don't want to reject the null, and the null is tested at 0.05 level. So you will compare this p to your alpha, alpha being 0.05. If this is larger than your alpha, then you fail to reject the null. This is, in fact, larger than the alpha. So we are failing to reject the null. We actually are happy that we don't get to reject the null because it means that our variances are, in fact, considered equal, meaning we did not violate the assumption for t-test. Again, the assumption for independent sample, one of the assumptions for independent sample t-test is that the variances are in fact equal, and they are. And because they are equal, we can read this top line for the t-test. Your t-test starts right here in this place where my cursor is. So the t-test starts here. And because we failed to reject the null on Levene's test, we get to read this t statistic. So that's important statistic. The t is 4.607. The degrees of freedom are 272, and the p is 0.00, which is never 0, so we double click if that works. Apparently it doesn't. Oh, there it is. My table disappeared. There it is. So it's 0.000006, so it's less than 0.01. You can just round it up, way up. 0.01. And if our test was also at 0.05, alpha 0.05, then we know that this p, and this is a two-tail test, so we keep it two-tail. It's non-directional, so it's two-tail. The p is less than alpha, so this is less than 0.001. Our alpha is 0.5, so that p is less than alpha. Our mean difference is 10. So we can, in fact, reject the null, reject the notion that male and female work the same amount of time in the industry. So, in fact, there is a difference between males and females. And then you can really go back and say, okay, so now that we rejected the null, so there is a difference in the years of working in industry. Where is the difference? And you can then go back and look at the mean and say, okay, male statistically have worked longer in the industry than females. And there can be several reasons for it, but that's really not about this. But since it is a supply chain, it is simply, and it is a male-dominated industry, according to our chart, at least in this situation, that maybe there are fewer females and that there have, there are probably, possibly, I don't know, younger, if it has been historically a male-dominated industry. But again, I don't know that. I'm hypothesizing here. What may be happening. This could be a basis for the next hypothesis to see if, in fact, females are younger than males. Okay, so that is sort of what you would be looking. So what is the conclusion? We reject the null. The interpretation is that males and females worked statistically different amount of years in the industry, and then sort of you can go back and say males work statistically more or for longer, have been worked longer, more years, not longer, but more years in the industry than females, based on this mean table. Okay, so that's it for the t-test. Now let's look at Anova. So let's look at the same work in the industry, but let's do Anova real quick. Again, I assume you know how to run it or why you run it. So I'm just going to be pretty quick on this. Let's just use education as our factor, and worked in the industry as our dependent variable. I will just do post hoc, and I'll just do, let's say, Bonferroni and maybe Tukey, Tamhain. And again, I assume you know what you're doing. This is a post hoc test. And I'm going to click all these. Again, I've created this for my student, Mercer University student, so they're so you guys are fairly ahead and you should know where you are. If not, send me an email and ask me questions. All right, so Anova. All right, here we go. So you have here compulsory school, college, university, and others. So we have 4 groups, potential groups. You see that the groups are unequal, which is not ideal, but it is what it is. Worked in the industry is our dependent variable. First thing, just like in the t-test, we want to test for homogeneity of variance. In case of, well, and here you can see that the mean for each level of education, the mean here is again in worked in the industry. So compulsory school on average have spent 27 years in the industry. So people with compulsory compulsory education spend 27 on average have spent 27 years working in industry. College 22, almost 23 years. University only 17, and then other 20, almost 23. So again, we're doing homogeneity of variance. It's 0.06, so if we compare it to our alpha of 0.02, I'm sorry, 0.05, alpha 0.05, compare this p to alpha 0.05. This one is larger, so we fail to reject the null. Again, this only means that homogeneity of variance is assumed, so the variances are considered equal. Because of that, we get to read the Anova table. Okay, Anova table, analysis of variance. This is where we determine, okay, is there a difference? So what would be the null hypothesis for this? The generic null hypothesis would be that there is a difference between levels of education in terms of years worked in the industry. Okay, so we said that before we actually start reading all these tables. So we're trying to determine if there is a difference between educational people with different education levels in terms of years worked in industry. We determined that assumption for equality of variance is met thanks to Levine's test. So we get to read the Anova table. And our P here is again less than alpha of 0.05. So this P is less than 0.001. So we're comparing between the groups. And so P is less than alpha. We reject the null. The null was that these the different levels of different groups with different levels of education. The null would be that they've worked equal amount of years in the industry. So the null would be that they've worked equal amount of years. But according to this table, this is not possible. So there is some difference. Now let's look at the difference. So since we have failed to reject the null on Levine's test, meaning equality of variance can be assumed, we read the omnibus test of Anova, which helped us to determine that there is a difference. So we rejected the null. And now we want to do a post hoc test where we find out where is the difference. Okay, where is the difference in years of worked in industry? So let's pick maybe you could look at Tukey or Bonferroni. I'll just pick Bonferroni. So here for Bonferroni, I have here 4 groups. And what I do a pairwise sort of comparison. Again, I look at P level, which is a third sort of column of numbers. So 1, 2, 3. So I'm looking at Bonferroni, third column, 1, 2, 3. And I can see that less than my 0.05 alpha is this university. This university is being compared to compulsory school. So you know that compulsory school and university are different. What's the difference in 10 years? And you can go back sort of and see, okay, 10 years, which direction? So you can see that compulsory school have worked on average 27 years, whereas university on average 17. So there's that 10 years difference. And according to Bonferroni test, post-hoc test, this difference is statistically significant, okay? So let's see if there's anywhere between college. So college and university, oops, I jumped around a little bit here. College and university are also statistically different, and the difference is 8 years. So if you want to go back to this main table again, so college and university, again, college, almost 23 years, whereas university is still about 17. So if you're in college, you got 3-year college degree, then you got more years in the industry under your belt, statistically speaking, than people who got their university degree. And yeah, so university is different from compulsory and college. Again, you can see the same findings sort of repeat itself as above because it's the same pairs. So we just found 2 pairs being different. University different from compulsory. 10 years difference where compulsory have worked 10 years more than university on, average statistically speaking. And then 8 years different with college and universities, also statistically significant. All right, so that's your post-hoc test. So first, Anova helped you determine that there is in fact a difference between the groups in terms of years worked in industry. And then the post-hoc test has helped you determine where is the difference. You can read either Tukey or Bonferroni if your Levin's test has been statistically not significant. If it is statistically significant, you would read Temhain. Okay, so if your variances are not assumed equal, you would read Temhain, but the findings are really the same in this case. Okay, so that is it. This sort of should help you determine, help you sort of how to read the tables, how to reject or fail to reject and all. And the last thing I would ask myself, why is that this difference, right? Perhaps simply that somebody who got the university degree just spent more time at school, therefore they had less time for working in industry. That's a plausible explanation for the findings, right? So every time I run data and I have findings, not only do I just reject or fail to reject it all, but also I want to ask myself, what does it mean for the business and why may this be happening? So that's sort of a question that you should ask yourself, because from those questions you may come up with new hypotheses to sort of better understand a certain phenomenon. So that is it for today. I hope you found this sort of step-by-step how to read tables helpful, and feel free to ask me questions if you have any. Have a good night. Bye.